Yeah.
Okay, we're a few minutes late, so we should probably get started. This afternoon, we start with a talk from one of our sponsors, Lime Microsystems. Then we will split into 3 parallel tracks with talks in here and the EDIS RF NOC tutorial in one of the rooms outside. And in the other room will be general tutorials. And that will be this afternoon, and then we'll move to a break. And for our first talk, I'd like to introduce Borko from Lime, and he'll be talking about digital predistortion.
Thank you very much. Let me introduce. I'm Borisav Jovanovic. I'm from Lime Microsystem, and I will present you some achievements we made in our company. Topic of today's presentation is Lime's open source adaptive digital predistortion, which is applied to high power amplifiers. So let me start. This is the table of contents. I will talk about all this stuff which is presented in this figure. Power amplifiers may, as you know, they're non-linear devices, and their linearization is important for several reasons, for many reasons. For example, when speaking about RFPAs, linearization improves power efficiency and reduces running cost of wireless infrastructure. So, as you know, key metrics for characterization of power amplifiers are EVM and ACPR. And by linearizing of power amplifiers, we can significantly improve that characteristics. So ACPR is reduced, EVM is improved, and therefore we can support multi-carrier signals, high bandwidths, and allowed sophisticated modulation channels. So I'm here to present you Lime's solution for PA linearization, which is based on adaptive digital predistortion. So it is important to say that completely open source solution, which you can download from LimeNet application store or is available also on GitHub. So that's the policy of our company to give everything you want as open source, so you can just download it and use it for free. I have to mention also that we are implementing this digital predistortion to be available also as a part of GNU Radio software, but that will be completed by the end of the year. So for now, it's in phase of implementation. Why is the predistortion is important? You can get a greater range with your base station. Basic structure of predistorter model is based on indirect learning architecture, which is shown in this picture. Not all components are shown. Some are missed for simplicity. So the structure is composed of 2 main blocks, as it can be seen on figure, predistorter and postdistorter block. Predistorter simply drives the power amplifier, and postdistorter is trained to be inverse function of power amplifier. Just predistorter is simple copy of postdistorter block. At the end of training process, we obtain equality between signals at the input of predistorter block and also on PA output. Therefore, we achieve linearization and significantly improve ACPR and EVM characteristics of power amplifier. During the process of training, we try to find difference between predistorter and postdistorter output, and the difference is going to be minimized by training algorithm. When system is converged, we got 0 error and equality in signals at inputs of both predistorter and postdistorter, as well as at its outputs. Our algorithm, Lime ADPD, is based on modeling of a nonlinear system, such as a power amplifier and its inverse. And this is modeled by complex valued memory polynomials, which are in fact cut version of Volterra series. For a given complex input, x, we obtain a complex valued memory polynomial output, which is given by a question which is presented in a slide. So in complex value memory polynomial model takes into account both system memory nonlinearity effects as well as memory effects. As you can see in those equations at the bottom, n denotes memory length and m denotes nonlinearity order. In equation, coefficients are denoted by A, and there are two cases for envelope, to use complete form or to use even order terms only. Well, in fact, we after a thorough simulation, we have chosen even order terms only envelope, since it's very simple to calculate and it provides better results. Our predistortor model can be described by a set of equations. So at the top of the slide, equations describe the predistortor model. After that, following equations describe the posistortor. So the model is the same. Also, predistortor and posistortor shares the same set of complex coefficients. Also, model accounts for delay line, because in ADPD loop there is delay line. We have ADC, transmitter chip, PA, coupler, also receive chain. So delay line should be accounted and also imported into the model. Well, our training algorithm simply changes the complex valued memory polynomial coefficients in order to minimize the difference between the outputs of predistortor and postdistortors. These signals are denoted with the YP and Y signals. So we find instantaneous error, and then we do the training. It's done by minimizing recursive least square error, which is given by the equation at the end of the slide. In this equation, parameter lambda is a forgetting factor. It's a number which is close to 1. So, as summary, predistortor and postdistortor are nonlinear adaptive filters. Two choices are considered to have complete form or even order terms only, and we adapted for implementation even order terms only to save hardware and to make our implementation more power efficient. Recursive least square error is minimized by solving a set of linear equations. There are many equation solver candidates, such as LU decomposition, Gauss-Seidel, gradient descent. The former two are iterative techniques, but we choose LU decomposition because it's fast to be implemented. It's very fast compared to other techniques, and we get better tracking of ADPD loop. Implementation. Well, we have implemented our ADPD algorithm for PA linearization on our Lime SDR QPCI Express board. This board is basically 4x4 MIMO board, and it offers many possibilities. It covers very large, very wide frequency range, up to 3.8 gigahertz. It has two transceiver chips, called LMS7002M, and each chip is 2 transmit, 2 receive. So it's 2 by 2 MIMO. That board is used for predistortion, for implementation of predistorter block. In fact, the board offers many possibilities. Many of them are not used, and for simplicity, only necessary components are given in the slide. Besides transceiver chips, FPGA boards has FPGA chip, Cyclone 5, Altero Cyclone 5, which is used for implementation of predistorter block. Also, the board provides arbitrary waveform to be loaded. So for purpose of demo and testing, for example, LT waveform or WCDMA waveform can be loaded into FPGA and can drive the predistorter model. So predistorter has provision for SPI interface in order to update its coefficients. Well, the board itself is connected to the CPU core over a dedicated PCI Express interface, and CPU core implements, in fact, post distorter and delay line and the rest of the training algorithm. So all the calculation is done outside the board. Predistorter only is implemented within the FPGA. In order to calculate coefficients, CPU core needs waveforms, and waveforms are captured by dedicated data capture RAM blocks, which are given on the left side of the picture. So predistorter takes a signal from some waveform RAM block and produces the output which drives transceiver chip LMS7002M, exactly its transmitter path. Well, waveforms at the input and output of predistorter, as well as from the output of PA from power amplifier, are captured, and that waveforms are brought together to CPU core, to dedicated software which is used for calculation, and it exactly finds new components and over PCI Express interface loads them into the predistorter model. So in every adaptation step, predistorter obtains new coefficients. Conversion from baseband to RF is done by LMS7002 chip over its transmitter path. Down conversion from RF to baseband is done using receiver path. In fact, there is one receive path called ADPD monitoring path. In case of MIMO applications, when we have multiple PAs, we can use several transmitter paths, but only need one receive path, which is used as a time-sharing resource. So at one moment, at one time, one PA is being linearized. Well, for real application, we don't need waveforms, and we don't need XP signal waveform bringing to the software. Just we need to have some real waveform. Our CPU core implements, for example, LT stack, and it acts as some kind of digital modem, and data is simply loaded from the CPU core over PCI Express interface, and that data is fed to the input of predistorter. Well, our board has one more provision. We have, in fact, option to use on-chip 12-bit data converters, ADC and DAX. And the other solution is more, I think, important for predistortion. There is option to use 14-bit DEX and ADCs, which are positioned, mounted on the board, they're external components. So with 14 bits, we get the better results, lower ACPR, and also lower EVM of signal when linearizing is performed. So that is the block diagram of our 4x4 MIMO board, Lime SDR, which is used for ADPD implementation. Additionally, there is GUI, which implements graphical display for demo and debugging purposes. GUI is capable to show important signals, for example, at predistortor, postdistortor inputs and outputs in time domain, frequency domain, and time constellation domain. Okay, now I will focus on measured results. It's important to say first, before implementation and measurements, our algorithm has been thoroughly simulated, and I will present you only the measured results. So we had 3 cases. Test case 1, we use power amplifier, maximum integrated, that is moderate output power amplifier with saturated power of 19 dBm. For test case 1, we used single carrier WCDMA test model 1 with RF center frequency 2.14 GHz. For test case 2, we used a little bit stronger amplifier, class J GAN HAMT amplifier with saturated power 40 dBm with drain efficiency of 70%. And for that case, we use also single carrier WCDMA test model 1 as input signal. RF center frequency is set to 1.5 GHz. And for test case 3, we try to linearize. In fact, we linearized our own amplifier, the amplifier which is product of our company, developed by our company. It's called LMS P10C. It covers frequency range from 2.1 up to 2.6 GHz. It's 10-watt power amplifier module, and we used for its linearization 20 MHz and 10 MHz LT test signal. RF center frequency, carrier frequency, was set to band 7, 2.675 GHz. Well, I will present you results from test case 1, moderate output power amplifier with saturated power 19 dBm, test signal VCDMA test model 1. So this is the screen capture from software, from Lime Suite software. That are the signals from the beginning, before training algorithm has been done yet, and predistortor signal are equal. So predistortor is just bypassed at the beginning. Signal X in plot 3, as you can see, is quite distorted. It is the measure of PA output, and we obtain complete misalignment between predistortor and postdistortor output signal. It can be seen in plot 2. We got very huge error, which is going to be minimized using our open source algorithm. So after training, signal at predistortor output is predistorted in order to cancel PA distortion components. Now, X is a measure of PA output, is linearized, and that can be seen on figure 3. We got now excellent matching between output signals of predistorter and post-distorter. The signals can be seen on plot 2, and improvement leads to the zero error, which is given in plot 4. So improvement of PA in linearization can be seen by comparing the spectra of output signal of predistorter compared to the PA output X. So these results are obtained by spectrum analyzer. Yellow trace represents the spectrum of signal at PA output without ADPD, and with blue trace is with ADPD. As you can see, IMD3 and IMD5 distortion components at PA output can be reduced by almost 20 dBs. Without predistortion, we obtained ACPR of minus 34 dBcs, and with predistortion, our result was ACPR is minus 51 dBcs. Therefore, we obtained 17 dBcs in ACPR. Regarding EVM, before predistortion, initial predistortion EVM was 6.58%, and after we started a DPD algorithm, obtained EVM was only 3.24. So by using this algorithm, you can significantly improve your signals and get the greater range or your base stations. Test case 2 is class J GAN HEMT amplifier, which has two stages. So the first stage is based on max 2612 preamplifier, and the second stage is GAN amplifier with drain efficiency of 70%. Total saturation power was 40 dBm, and for that test case, we use WCDMA test model 1. These are the results. Before ADPD was started, ACPR was minus 43 dBcs, and after predistortion has been completed, it was reduced up to minus 53 dBcs. And the last test case, it's our own amplifier model designed for frequency ranges from 2.1 up to 2.6 gigahertz. It's 10-watt power amplifier with 30 dBm output modulated power. We used test signals 20 megahertz and 10 megahertz 2x2 MIMO LT signal. Board itself, amplifier itself consists of two printed circuit boards. One is control board, including the DC-DC converters, and the other board has amplifier stages. There are two amplifier stages. Both stages produces the 30 dBm modulated power, and layout of the board is given on the right side of the slide. Beside RF in and RF out connections, there is also one coupler output, which is used for predistortion to obtain PA output signal. These are the specifications of developed amplifier module. Output 1 dB compression point is 38 dBm, and gain is 45 dB, and it consumes only 500 milliamps at 30 dBm, 20 megahertz LT modulated power. Power supply, voltage supply is 12 volts. So these are the results for 20 megahertz LT case. Without ADPD running, at start we had minus 39 dBcs, and after, when ADPD was completed, minus 49. It is improvement of 10 dBcs. Also, at the beginning, we have EVM 5.33%. After DPD was running, it was improved to 4.48. In the other case, we used different signal, but the same power amplifier. Signal was now 10 megahertz LTE, and in that case, with ADPD, ACPR was lowered to minus 51 dBcs. Also, EVM is also improved. So our Lime ADPD algorithm has been implemented and verified by measured results. I must emphasize that it is capable to remove any distortion above system floor noise, DEX, TX, PA, coupler, RX, and ADCs. So we have 3 test cases covering different amplifiers, covering different carrier frequencies, covering also different modulations. And for all cases, we achieved significant improvement in both EVM and ADPD. So this algorithm is open source. It can be downloaded from LimeNet application store, and it can be used in our works. So, as summary, these are the results for different cases. As it can be seen in this table, we use different modulations. We use different amplifiers with saturated powers. We change the RF center frequencies, and for all cases, we obtained significant improvement. Well, thank you very much for listening.
Okay, we'll have time for a question while Fred gets set up for the next talk. So does anyone have a question? Do we have the microphone? Excellent.
Yeah, so this design requires a coupler on the output. How much are you losing in power on that? And is that factored into your measurements?
Well, if you have input signal which is modified to accomplish with average signal to peak power ratio, you cannot lose any power. You even cannot lose 1 dB in power. Everything is up to the input signal. Okay.
We have another question, I believe. We have another question. Just stand to one side.
Okay. Okay.
Hi. Over here.
That's it.
So, excuse me. So you said you had, yeah, your EVM improved quite a bit, but why was the EVM high in the first place? Like, how much CFR were you running, or? Is that due to the
limitations which are limited by hardware? So as much as possible, we reduced EVM. The last case is for 20 megahertz LT signal, so it is enough, I think.
Okay, so I mean, even before DPD, your EVM was pretty high.
Yes.
And after DPD, it improved quite a bit, but with 64
well,
QAM signal that you were showing.
Up to some components which has phase noise. By replacing that components, we can obtain lower EVM.
Okay.
Okay, I think that's going to wrap it up, and we'll move directly into the next talk.
Okay.
Thank you.
Thank you.
We'll move directly into the next talk, which will be